Good day, viewers all over the world. I welcome you to today's class. We shall be continuing with our teaching on Introduction to Matrices, Part 2. In our last class, we looked at Introduction to Matrices, Part 1. So we shall be continuing today. We stopped at the determinant of a 2 by 2 matrix. Today we shall be continuing with the determinant of a 3 by 3 matrix. Please, if you have not subscribed to my YouTube channel, please subscribe to my YouTube channel, like my videos, share them in your social media platforms, make comments for improvement, and as you do, God will bless you on every side. My name is Dr. Chris Esekaibe. I am the chief lecturer in one of the most prestigious polytechnics in Nigeria, and I am a specialist in numerical analysis, data analysis, and modeling, scientific computing, and statistical analysis. I hold a doctorate degree in mathematics, a master's degree in mathematics, and a bachelor degree in statistics. I specialize also in training AI models. If peradventure you are an AI firm, you have models to train. I've worked with 2 US firms where I assisted in training their AI model on mathematical algorithms. If you want me to be part of your team of mathematicians and statisticians, why not? You can contact me and I will be glad to be part of what you are doing. My contacts are here. This is my contact, or these are my contacts. This is for call on WhatsApp +234 8033021903. Then the second one is for call only +234 7066 297535. And my email address is chrisdavis2015@gmail.com. I will be looking forward to hearing from you. If also you are a research institute, why not we can work together as a team? For the sake of time, permit me to clean this part of the board so that we can go into the business of the day. We have a whole lot to cover today. Please watch patiently as we try to see how we can calculate the inverse of a 3 by 3 matrix and so on and so forth down to the end of the class. We are looking at determinant, inverse, and application of matrices. Now, we want to start with the calculation of the determinant of a 3 by 3 matrix. If, for instance, if A equals 3, 3, 5, 3, 5, 9, 5, 9, 17, and we are now told to find the determinant of A, find determinant of A. Some authors write it as A in absolute value. Please note, before we start this, we need the matrix of signs. Matrix of signs. Matrix of signs. This is a 3 by 3 matrix of signs. It helps in calculating the inverse. It also helps in calculating the matrix of cofactors. If it is a 4 by 4 matrix, you also write out the matrix of signs. So we call this matrix of signs. Matrix of signs. So you can see plus, minus, like that. It goes like that. So now, for this particular matrix, calculating the determinant is easy. So we are going to break it down. So determinant of A will be equal to, we start with the first one, there is 3. Now you roll out this row and roll out this column. You write 5, 9, 9, 17. Then of course the second sign there is minus 3. Then now 3 is in this column and in this row, so you have 3, 9, 5, 17, 3, 9, 5, 17. Then of course the next sign is plus, which is +5. Then you roll out this particular column and you roll out this particular row. So you now have 3, 5, 5, 9. So having this, you will now come and have 3 into, of course, you now take the determinant of each of the minor. 17 times 5 will give you 85. Minus 9 times 9 will give you 81. Then minus 3 into 3 times 17 will give you 51. Minus 5 times 9 will give you 45. Then plus 5 into 9 times 3 is 27. Minus 5 times 5 is 25. Then you close the bracket. Then you now have 3 into 85 minus 81 is 4. Minus 3 into 51 minus 45 is 6. Then plus 5 into 27 minus 25 is 2. So you are going to have 12 minus 18. 12 minus 18 plus 10. So is 4. So determinant of A is equal to 4. That's what we have. So having that, we are now going to look at the minor of a matrix. Let's take a little heading. The minor of a matrix. Now, for instance, if I have a matrix, if A equals A11, A12, A13, A21, A22, A23, A31, A32, A33. Now, this is a matrix, a 3 by 3 matrix A. Please note you can only get the determinant of a square matrix, whether 2 by 2 matrix, 3 by 3 matrix, 4 by 4 matrix, and so on and so forth. Now, if we want to write the minor of A11, now note every element here has a minor. What this simply means is that this is A11. If I want to get the minor, I will not consider the elements on the rows where A11, on the row where A11 is, and the elements on the column where A11 is. So this and this will be rolled out. So I'm going to have A23, A22, A23, A32, and A33. This will now be the minor. Some authors take it as determinant. You now take maybe the determinant. This will now be A22, A33 minus, of course, this and this, A23, A32. So this will now be the minor of the element A11. Permit me to clean this part of the board so that we can have space. The determinant of that particular matrix is 4. Take note of that particular matrix. We may definitely come across it again. Now, if I want to take the minor of A22, the minor of A22 is, look at it now, this is A22. We are not allocating any sign to it. This is A22. So we are going to have it like this. Look at where A22 is on this column and this row. So this column and this row will be rolled out. We are going to have A11, A13, A11, A13, then A31, A31, A33, A33. Then we can now write it as this, bracket open, this are the elements on the main diagonal. We are going to have A11 multiplied by A33 minus, of course, the other diagonal, A13 minus A13, A13, A31. So this is now what you are going to have. Now also, if I want to get the minor of maybe A33, for instance, A33. Of course, Look at A33 here, it's on this particular column and this row. So this column, this row will not be considered. We are going to consider A11, A12, A21, A22. So we are going to have A11, A12, A21, A22. Then you can write it as A11, A22 minus A12, A21, and so on and so forth. So that's how we consider the minor of a matrix. So the minor of a matrix, of course, the matrix must first of all be a 3 by 3 matrix before you can begin to get the minor of each element in that particular matrix. So the minor of a matrix is a 2 by 2 matrix that can be obtained by omitting the row and column containing the element that is concerned in a given matrix. I come again. The minor of a matrix is a 2 by 2 matrix that is obtained by omitting the row and column containing the elements concerned in the given matrix. Just like the same way we have our A11 as the element of interest. So the row where A11 is and the column where A11 is will not be put into consideration, will be cut off. So you now have the remaining 2 by 2 matrix A22, A23, A32, A33. That's what we have there. Then you cannot find their minor determinant. Also, if you want to get for A23, okay, let's go for A23. So the minor for A23 is as simple. This is where A23 is. This row will not be considered, it will be omitted. This particular column will also become omitted. So you have A11, A12, then of course this down one here, A31, A32. So you come like that. You are not going to multiply out. You have A11 multiplied by A11, A32 minus, of course you have A12 multiplying A31, and so on and so forth. It goes like that. So now this takes us to another sub topic in matrices. Let us consider the cofactors of a matrix. The cofactors of a matrix. Permit me to clear this part. The cofactors of a matrix. The cofactors of a matrix. So we just consider the minors. Now we are looking at the cofactor. It is good you understand all these. The cofactors of a matrix. So now, if we have that same matrix A, if we have that same matrix A, permit me to write it again. A is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. Now, when you are dealing with the cofactors, you make use of the matrix of signs. You can see now this is a 3 by 3 matrix. Then we have a 3 by 3 matrix of signs. If you are dealing with a 4 by 4 matrix, of course you are going to have a 4 by 4 matrix of signs. Now we want to see how we can get the cofactors of a matrix. Now the cofactor of A11 will now be, look at it now. The first thing you do, A11 is at what position here? So it is plus. So you have to put the plus sign there. Then you now write, you rule out the row and the column where A11 is, and write out every other element. It will now be A22, A23, A32, A33. So having this, you are going to have plus into A22, A33. You multiply like getting the determinant, then minus A23, A32. So this will eventually become the cofactor of that particular element. Now, if we want to get the cofactor for A21, let's get the cofactor for A21. Cofactor for A21, of course, that will be A21 is equivalent to a negative sign, so you put it here. Then this particular row will go, this column will go. You are going to have A12, A13. Of course, this row will go, this column will go. So you have A32, A33. So the cofactor will now be minus into, you get the determinant. These are the elements in the main diagonal. This will be A12 multiplied by A33, A12, A33 minus, of course, A13, A32. Then you close the bracket. Now let us take one more example. Let's see cofactor. Let's see cofactor for, okay, let's take A32 for instance. A32. Now this will be equal to, look at the position of A32 here is negative. So you have to put the negative sign first. Then A32, this particular row will be omitted. This particular column will be omitted. This particular row will be omitted. So we are going to have A11, A21, then of course A13. Then we now have A13, of course this and this will go, since for A32, A13, A23, A23. So by the time you now take this, will now be equal to minus into A11 times A23 will be A11, A23 minus A13, A21. That is how it goes. So this is how we calculate cofactors for each element. Now, it is good we say the uses, we explain the uses of determinants. We defined a determinant the other time to be a single value that represents a matrix. A determinant is a single value. I mean to also clean this. We are still going to be using the matrix of signs for inverse and adjoint and the rest of them. So let us see some uses of determinant. Uses of determinant. Uses of determinant. Now the first use, determinant is used for ranking a matrix. One, it is used for ranking a matrix. Then two, it helps to tell whether a matrix is singular or non-singular. It tells whether a matrix is singular, so is singular or non-singular. So, in our last video, I defined what a singular matrix is. A singular matrix is a matrix whose determinant is equal to 0, while a non-singular matrix is a matrix whose determinant is not equal to 0. Another thing that the determinant is useful for is that it is used to determine the inverse of a matrix. It is used to determine the inverse of a matrix. That is what it is. Then, fourthly, these 4 points will be good. It is used to solve simultaneous linear equation. It is used to solve simultaneous linear equations. So that is what these are the 4 uses of determinants. Now, let us see how we can calculate the rank of a matrix. It's a subtopic. Every matrix has a rank of every square matrix of a matrix. So, if you want to calculate the rank of a square matrix, we make use of the determinant, just like what we said here in one of the uses of the determinant. Every square matrix has a rank. If the rank of a matrix is defined as the order of the largest non-zero determinants that can be formed from the elements of the given matrix. If, for instance, if I have matrix A, if A equals 6, 9, 4, and 11. Determinant of A is equal to 66 minus 36. That is 6 times 11, 66. 4 times 9 is 36. And that will be equal to 30. So you can see that the first thing here is that it means that A is a non-singular matrix because the determinant of A is not equal to 0. Now, since we have calculated the determinant, how do I now know the rank? Now say A, determinant of A is non-zero, comma. That means that the rank of A will now be rank of A will be equal to the number of rows in A. And how many rows does A have? 2. So the rank of matrix A, so you can write like this. Some others write it as rank of A will be equal to 2. So you are permitted to also write it like this. R means the rank of matrix A. So you can only get the rank of a square matrix. Now let us take the rank of another matrix. Permit me to clean the uses of determinants. I believe you have copied them. You can play the video again and again for better understanding. If I have a matrix, if B equals 2, 5, 4, and 10, for instance, determinant of B is equal to 20 minus 20, and that is equal to 0. 2 times 10 is 20, 5 times 4 is 20. Now, it means that B is a singular matrix. And now, how do we determine the rank of B? Look at the elements in B. They are not 0. All the elements are not 0. So since B, the determinant of B is equal to 0, then B is a singular matrix. So it then means that B, the rank of B will now be reduced to 1. So the rank of B, let us write it like this, rank of B will be reduced to 1. Why is it 1? Because first, the determinant of B is 0, B is singular. Then, we only reduce it from 2 to 1 because the elements of B are not 0. If the elements of B are 0, then we can now say that the rank of B is 0. So we reduce it by 1 because the elements of B are not 0. They are 2, 5, 4, and 10. Now, let us take more examples. We are looking at the rank of a matrix. For instance, if C equals 0, 0, 0, 0, of course, the determinant of C equals 0 minus 0 is equal to 0. Again, C is singular. It's a singular matrix. And now, because all the elements of matrix C are 0, then the rank of C is 0. All elements of C are 0, then this implies that the rank of matrix C is equal to 0. Now let us take another matrix. If D equals, let's take a larger matrix now, maybe a 3 by 3 matrix, 1, 1, 2, 8, 4, 7, 6, 4, 7, 6, 9, 5, 3, 9, 5, 3. If D is equal to this, now determinant of D will be equal to 1 into, of course, if you take 1, this will go, 3 times 7, 21 minus 5 times 6, 30. Okay, then of course minus 2, we are using the matrix sign, the sign of the matrix, so 2 here is negative, so this will go 4 times 3 is 12, this will be 12 minus 9 times 6 will be 54, minus 54, then of course plus 8 into this will go 5 times 4 is 20 minus, then 9 times 7 will be 63. So when you come here now, of course 21 minus 30, of course times 1 will be minus 7. Then of course 12 minus 54 multiplied by 2, you are going to have 84, of course, plus 84, then 20 minus 63, then multiply the answer by 8, you are going to have 344, that's plus, you have that will be minus 344, minus 344, then when you take this, you are going to have minus 267, and of course it's not equal to 0. So D is non-singular, and again the rank of D, this means that the rank of D equals to the number of rows in D, and that is equal to D is a 3 by 3 matrix, it has 3 rows, and that will be 3. So rank of matrix D will be equal to 3. It's as simple as that. So the rank of matrix D is 3, because if the determinant of the matrix is non-zero, that means it's non-singular, then the rank of that matrix will be equal to the number of rows in that particular matrix. Now let us take another example again of the rank of a matrix. Let's see how it goes. Let's take another example so that you will have a better understanding of what the rank of a square matrix is. So note, you only get the rank of a square matrix. If I have another 3 by 3 matrix, E equals, this time around, 3, 4, 5, 3, 4, 5, 1, 2, 3, and 4, 5, 6. 4, 5, 6. Of course, the determinant of E will be equal to 3 into, of course, this part will go, this part and this part will go, so you have this and this 6 times. 6 times 2 will be 12, minus 5 times 3 will be 15, Then of course, then the next second one is negative, that is minus 4 into this will go 6 times 1 is 6 minus 4 times 3 is 12. Then of course the last one is plus 5 into this will go, this will be 5 times 1 is 5 minus 4 times 2 is 8. Then you cover the bracket. So you are going to do a little of arithmetic, and as such you are going to have the determinant of E is equal to 12 minus 15 is minus 3 times 3 is minus 9, 6 minus 12 is minus 6 times minus 4 plus 24, 5 minus 8 is minus 3 is times 5 is minus 15. Then you take this little arithmetic, minus 9 plus 24 is 15. Then 15 minus 15 is 0. So you can see that the determinant of E here is 0. The determinant of E is 0. Now, if the determinant of E is 0, we don't just conclude that, of course, E here is singular. Matrix E is singular. It's a singular matrix because its determinant is 0. So we cannot just come as, okay, we now reduce the rank to 2 because it has a 0 determinant and the number of rows is 3. But what we need to do, we need to try one of the other minors. Take the determinant of at least one of the minors there. Let us try 2, 3, 2, 3, 5, 6, 5 and 6, and see if we also get 0. If at least one of them is not 0, then we just reduce by 1. 6 times 2 will be 12 minus 3 times 5, 15. That is minus 3, and that is not equal to 0. So we cannot conclude that the rank of matrix E is 0. So since it has one minor that has determinant that is not equal to 0, so the rank of E will now be reduced to 2. So rank of matrix E will be equal to 2. That is so once it's a 3 by 3 matrix and you see that the determinant is 0, then you take one of the minors from any part of the matrix. You can even take this one. You can take 3, 4, 3, 4, 1, 2. Any part, any minor. 2 times 3 is 6. 1 times 4 is 4. So this is also 2. So it's not also equal to 0. So that's why the rank can only be reduced to 2 and not 0. So, beloved, I believe you have seen how we can calculate the rank of a square matrix, and we have been able to see the uses of determinants. Now, let us go to the inverse of a matrix. Of course, without the adjoint of a matrix, it will be difficult to calculate the inverse. So let us go straight to the inverse of a matrix. You can only get the inverse of a square matrix. And listen carefully. A matrix whose determinant is 0 does not have an inverse, because you have to divide every element of the adjoint of the matrix to get divide every element of the adjoint of the matrix by the determinant to get the inverse. So if the determinant is 0, division by 0 is not applicable in mathematics, is error. So any matrix, square matrix whose determinant is equal to 0 does not have an inverse. So now we are looking at the inverse of a matrix. So we are going to be using this matrix of signs, but let us start with a 2 by 2 matrix first. For a 2 by 2 matrix, now I pick an example strictly. If A equals 2, 4, and 6, and 20. Now the first thing we need to do is to get the determinant of A. will be equal to 20 times 2 will be 40 minus 6 times 4 is 24, and that will be equal to 16. So the determinant of A is 16. Now if I want to get the adjoint of A, the adjoint of A for a 2 by 2 matrix, please watch it. You interchange the elements in the main diagonal. These are the elements in the main diagonal. You bring 20 here, you bring 2 here, then you assign negative sign to the elements in the other diagonal. I come again. If you want to get the adjoint of a 2 by 2 matrix, the first thing you do, interchange, let me write it here, interchange the element in the main diagonal, then multiply the element in the other diagonal by a negative sign. That means a minus sign. That is what it means. So look at the matrix A here now. You have to interchange the elements in the main diagonal. So the position of 2, this other element in the main diagonal will come and take that position. 2 will also come and take the position of 20. That's how you have 20 and 2. Then the other diagonal, every square matrix has 2 diagonals, the main diagonal and the other diagonal. So now when you interchange the elements in the main diagonal, you assign or you multiply the elements in the other diagonal by a negative sign. So that's why you see minus plus 4 becoming a minus 4 when multiplied by a minus sign, then plus 6 becoming minus 6. So that is the now the inverse of A is written as A inverse, that's how we write it, is given as A inverse equals 1 all over determinant of A times the adjoint of A. So A inverse here will be equal to, what is our determinant? 16. 1 all over 16, bracket open, the adjoint is 20, minus 4, minus 6, 2. So it means you are going to use 16 to divide every element there. So this will be 20 over 16, this will be minus 4 over 16, this will be minus 6 over 16, this will be 2 over 16. Then simplifying further, 20 over 16 definitely will be 5 over 4, dividing the numerator and denominator by 4. You have 5 over 4. 4 over 16 will be minus 1 over 4, minus 6 over 16, of course, divided by 2. We are going to have minus 3 over 8. Then this will be 1 all over 8. So this will now be the inverse of matrix A. So that is how you calculate the inverse of a 2 by 2 matrix. That is how you calculate the inverse of a 2 by 2 matrix. Now we want to see how we can calculate the inverse of a 3 by 3 matrix. And we highlight the steps, then we take a practical example. Permit me to clean this part of the board, and we highlight the steps for calculating the inverse of a 3 by 3 matrix. Then we implement using a particular problem. We solve using a particular problem to demonstrate. Now the inverse of a 3 by 3 matrix, Here we go. The first step is, now let us see the steps involved. 1. Calculate the determinants of the matrix. If the matrix is A, for instance, determinant of A must not be equal to 0. If determinant of A is 0, of the matrix is 0, you cannot proceed because division by 0 is not acceptable in mathematics. Then step 2, get the matrix of cofactors, capital letter C. Then 3, transpose the matrix of cofactors to get the adjoint. That means our adjoint of maybe the matrix A will be equal to C transpose. Then the last step, divide each element in the adjoint of A by the determinant. Those are the 4 key steps in calculating the determinant of a 3 by 3 matrix. Please note the matrix of signs is very, very important. Now I take us with an example. Now if A equals 3, 3, 5, 3, 5, 9, 5, 9, 17, find A inverse. So the first thing we need to do is to get the determinant of A. What is the first step? That will, of course, will be 3 into, you're having 3 into this 3 here. Of course, this goes to 17 minus 5 will be 85 minus 9 times 9 minus 81. Then, of course, there will be a minus sign minus 3 into this goes, 17 times 3 is 51 minus 5 times 9 is 45. Then of course plus 5 into this row goes, this column goes. You have 9 times 3 is 27. 5 times 5 minus 25. So you go like that. This will now be equal to 3 into 81 minus 85 minus 81 is 4. Minus 3 into 51 minus 45 is 6, then plus 5 into 2. So this will be 12 minus 18 plus 10, and that is equal to 4. The determinant is 4. So you can say then we are now proceeding to step 2. Step 2 says we should get the matrix of cofactors. So I will need to clean this part of the board so that we'll have enough space to write. Now the matrix of cofactors, that is the main thing that is needed. That step is crucial and very, very vital. It's crucial and vital. Remember, we are looking for the inverse of A. Now, one thing you need to understand is that every element in A has a cofactor. Now we want to start getting the cofactors. We start with the first one for 3. We have, of course, we are using the matrix of signs. Matrix is in the positive position. This goes, this goes. You are going to have, you have 5, 9, 5, 9, 9, 17. So this will be equal to plus into 85. 17 times 5 is 85 minus 81. That will be equal to plus 4. So that's the first one there. Then of course for the next 3 again, for this other 3, this goes, of course, the sign there is minus. So you have minus into, for this other 3, this goes, you have 3, 9, 5, 17. 3, 9, 5, 17. So when you go, you have minus into 17 times 3 is 51. Minus 5 times 9 is 45. 51 minus 45 is 6. So you're going to have, because of the minus sign here, minus 6. Then for 5, you have the sign here is plus. Then this goes, you have 3, 5, 5, 9. 3, 5, 5, 9. So this will be plus into 3 times 9 is 27 minus 5 times 5 is 25. So you have 27 minus 25, you have 2. So it keeps going like that. You put it plus 2, write the sign in front of it. Then the next one here, let's come to this 3. For 3, we have, of course, is a negative sign. Then we are going to have, if this 3 is going, this is going to have 3, 5, 9, 17. 3, 5, 9, 17. So there's a minus sign there. 17 times 3, of course, is 51. 9 times 5 is 45. So that will give you minus 6. 51 minus 45 is 6 because of the negative sign in front. Then you get that. Then, of course, again, for this 5 here, for 5, of course, the sign here is plus. For this 5, this goes, you have 3, 5, 5, 17. 3, 5, 5, 17. So you have plus into 17 times 3, of course, is 51 minus 5 times 5 is 25. 51 minus 25, of course, is plus 26. Then permit me to come to this other side for, which other one now? For 9, of course, 9 has a negative sign. You have, for 9, this goes, this goes, this goes, this goes, 3, 3, 5, 9. You have 3, 3, 5, 9. This will be minus into 9 times 3 is 27. 3 times 5 is 15. So you are going to have 27 minus 15 is 12. So that will equal to minus 12. Then you come here again for 5. For this 5 here, this goes, and of course it's plus. You put it plus. For 5, this row goes, this column goes. You have 3, 5, 5, 9. 3, 5, 5, 9. 9 times 3 is 27, so it's plus into 27 minus 25. So that will give you plus 2. That is what you have there. Then the next one for 9. For this 9, of course, is minus you have there. For this 9, this particular column goes, this row goes, you have 3, 5, 3, 9. 3, 5, 3, 9. So you have minus into 9 times 3, 27 minus 3 times 5, 15. And that will give you minus 12. You have that. Then lastly, for 17, of course, you have the plus sign there, which is equal to this. So you have plus into this column goes, this row goes 3, 3, 3, 5. You have 3, 3, 3, 5, and that will be plus into 5 times 3 is 15 minus 3 times 3 is 9. So you're going to have plus 15 minus 9, you have plus 6. So you can see that we have been able to get all the cofactors for each of the elements in matrix A. Have it at the back of your mind, this is matrix A. Permit me to claim, we're already in step 2. Permit me to claim the the determinant. Of course, the determinant of A is 4. So now I want to write out the matrix of cofactors. Our C will be equal to, we are starting from here. It's going like that. This will be 4 minus 6, 2 minus 6 plus 26. Then the next one is minus 12. Then you have plus 2. Then you have minus 12. And the last one is 6. So this is our matrix of cofactors. We have been able to get our matrix of cofactors: 4 minus 6, 2 minus 6, 26 minus 12, 2 minus 12 and 6. Now getting the transpose of C transpose is equal to the adjoint of A. So our C transpose, now in our last video I explained the transpose of a matrix, like turning it means interchanging rows with columns or turning a matrix 90 degrees. You are just making every column to become a row. That is what it means. Now look at the first column here, you make it the first row. This will be 4 minus 6 and 2. Look at the second column, you make it the second row. Minus 6, 26 minus 12. Look at the third column, you make it the third row. 2 minus 12 and 6. So that is what you have. And you can see this matrix is a special kind of matrix. You can see that our C transpose is still the same thing as C. Our C transpose is still the same thing as C. Our C transpose is also the same thing as matrix C. So permit me to claim this part. We have been able to get the matrix of cofactors C, and then we have been able to transpose it. Now we want to go take the last step to get our inverse of A. The last step will be dividing every element in the adjoint by the determinant. So our A inverse will be equal to 1 all over 4 into our adjoint, which will now be 4 minus 6, 2 minus 6, 26 minus 12, 2 minus 12 and 6. So now writing it in full, A inverse, we are dividing each of them by 4. You are going to have 4 over 4 minus 6 over 4, 2 over 4 minus 6 over 4, 26 over 4 minus 12 over 4, 2 over 4 minus 12 over 4 and 6 all over 4. So doing this, we are going to have 1, 4 over 4 is 1, minus 6 over 4 is minus 2 over minus 3 over 2. Then 2 over 4 is 1 all over 2, which is 1 all over 2. Then minus 6 over 4 is minus 3 all over 2. 26 over 4 is 13 all over 2. Minus 12 over 4 will be minus 3. 2 over 4 will be 1 all over 2. Minus 12 over 4 will be minus 3. And 6 all over 4 will be 3 all over 2. So this is now our A inverse. It is as simple as that. So you can see we have been able to calculate our A inverse. So please take note of this. We are going to use this to solve a system. Now we want to apply this using the inverse of a matrix to solve a system of linear equation. So that's our A inverse. You will see we are going to keep that for the solution of the system we are about to solve. Now, it is not just enough to know how to calculate the determinant of a matrix, the uses of the determinant, the adjoint, the inverse. now how do I apply the inverse of a matrix, the determinant of a matrix? How do I apply them to solve real life problems? What are now their uses? If I now know how to calculate the inverse of a matrix, I know how to calculate the determinant of a matrix, I know how to calculate the adjoint of a matrix, of what use are they to me? Now, you know that real life problems can be modeled into system of linear equations, and they can now be solved using the matrix inversion method, or the matrix inversion method. Now, solution to system of linear equation using matrix. Now let's look at solution to system of linear equations using the matrix approach. Now I will pick, first of all, a 2x2 system. Now a 2x2 system, let me pick a simple 2x2 system. If I say solve 2x plus 4y equals 5, then the second equation, 6x plus 20y is equal to 8. Now, the first thing you need to do is to put this in a matrix format. You bring out the matrix, you have 2, 4, 6, 20. Then, of course, the unknown variables are x and y. Then the right hand side is 5 and 8. So this is equivalent to having the matrix A, then the vector x. When you have a matrix, you have two lines beneath it. A vector, you have one line, then is equal to the vector B, the right hand side. This is the format of the matrix format of a system of linear equation. I didn't tell us what a vector is. A vector is a special kind of matrix that can either have one row or one column. That is what a vector is. So you can say this is a column vector. The x is also a column vector. So a vector has either one row or one column. Now, you can see, since we have been talking about matrices, we didn't talk about division of matrices. There is nothing like division of matrices. For instance, look at this particular challenge here. This is AX equals B. We have to look for X. On a normal algebra, we just come and say X equals B over A. This is wrong. If, for instance, I have 2x is equal to 6, I can write x is equal to 6 all over 2 is equal to 3. This is allowed in algebra but not in matrices. What we do in this case of matrix, if we are looking for x, we invert A. So we now make our x to be equal to A inverse B. For A to go to the other side, we have to invert A. Are you getting me now? So that is how we do it. So getting the value for x, because x is the vector of unknowns that we are looking for here. So from here, this implies that our x will be equal to A inverse B. So you have to solve for the inverse of A. And what a joy, we already solved this problem before. Now our A is equal to 2, 4, 6, 20. And of course, we already got the determinant of A to be equal to 40 minus 4. 20 times 2 is 40. 6 times 4, 24 minus 24. And that is equal to 16. And we also got the adjoint of A. Of course, we already got the adjoint of A. So let me just write the A inverse. Okay, the adjoint of A will be equal to, you interchange the elements in the main diagonal, then you assign negative to the elements in the other diagonal. So our A inverse will be equal to 1 all over the determinant, which is 1 over 16, multiplying the adjoint, 20 minus 4 minus 6 and 2. So our A inverse, we already calculated it. If you have been watching this video from the beginning, our A inverse, we got our A inverse to be 5/4. Our A inverse from the 2 by 2 matrix, we have 5/4 minus 1/4, 5/4 minus 1/4 minus 3/8 and 1/8. This is what we got. Now, since we have this, it is simple to solve, to get the solution. It's very, very simple to get the solution. Now we can use this simple space. Now that since our x, which is equal to xy, the unknown, is equal to A inverse B. So that will now be equal to, what is our A inverse? 5/4 minus 1/4 minus 3/8, 1/8. Then what is our B? Our B is the right hand side, which is 5 and 8. So we are going to multiply. So look at it. I taught us matrix multiplication. B is a 2 by 2 matrix multiplying a 2 by 1 matrix. This is a 2 by 1. Of course, the vector is a special kind of matrix. Now, what is the condition for multiplication? If the number of columns, this is the number of columns in the first matrix, equals to the number of rows in the second matrix, then of course we produce. So we are going to have a 2 by 1 matrix as our answer, and that is what we are going to get. So we taught this during our calculation. So now let me write out the answer. So it means that our vector x, which is equal to x, y, will be equal to, look at it now, we are going to have 5/4 times 5 plus bracket minus 1/4 times 8. Then this one will be minus 3/8 times 5 plus 1/8 times 8 by matrix multiplication. So when you carry out that little arithmetic, you are going to have 17/4. You are going to have 17/4 and minus 7/8. So this means that our x is equal to 17/4, our y is equal to minus 7/8. That's what we have for this particular problem. 17/4. So you can check it out. You can check it out. Look at it here now. Here you have 2 into, what is our x? 17/4. Then plus 4 into, what is our y? Minus 7/8. Of course, you will get 5. Carry out the expression. Then for the second one, we have 6. So we are checking now 6 into x. X is 17/4. Plus 20 into y is minus 7/8. Of course, you carry out the arithmetic, you will get 8. It means we are good to go with the two answers. So our x equals 17/4 and our y equals minus 7/8. Just say 5/4 times 5, 25/4. Then of course minus 8/4. You carry out the arithmetic, you will get 17/4. Carry out the arithmetic too. Doing, of course, you know both mass, breaking the brackets. Then before carrying out the addition, then of course the other one you have minus 7/8. Now also, let us solve a 3 by 3 system and see what will come out of it. Permit me to clean the board. A 3 by 3 system. Let's solve a 3 by 3 system and let's see what will come out of it. A 3 by 3 system. the 3 by 3 system of linear equations. Let's solve it and let us see what will definitely come out of it. This approach is simple, using the matrix approach to solve a system of linear equation using the matrix approach. Now look at this particular system. Solve 3x1 plus 3x2 plus 5x3 is equal to 24. 3x1 plus 5x2 plus 9x3 is equal to 40. Then the last one is 5x1 plus 9x2 plus 17x3 is equal to 74. So this is a 3 by 3 system of linear equation. We want to see how this can be resolved using the matrix approach. Of course, we are going to write this out. We are going to have, of course, the matrix. We have 3, 3, 5, 3, 5, 9, 5, 9, 17. And of course, the unknowns, x1, x2, x3. Then of course, the right hand side, 24, 40, 74. So you have that. So this will be our A, and this will be our X, and this will be our B, is equal to our B. So what a joy! If you look at the determinant and the inverse for a 3 by 3 system that we did, we calculated the inverse of A. So from what we got before, this simply means that from here, our A inverse was already calculated, if you have been following the class, to be 1 minus 3 all over 2, 1 all over 2, minus 3 all over 2, 13 all over 2, minus 3, 1 all over 2, minus 3, and 3 all over 2. We calculated the inverse of this, and of course, that is our A inverse. Then, it simply means that from here, we can get, of course, our X will be equal to A inverse B. So our X, which is equal to x1, x2, of course, X is a vector, x3, will be equal to our A inverse is 1 minus 3 all over 2, 1 all over 2, minus 3 all over 2, 13 all over 2, minus 3, 1 all over 2, minus 3, 3 all over 2. Then B, our B is the right hand side, which is 24, 40, and 74. You have that. So carrying out this, you have our x1, x2, x3 will now be equal to, when you carry out this multiplication, you are going to have 24 minus 60 plus 37. Then the second one will be minus 36 plus 260 plus 260 minus 222. Then the last one will be 12 minus 120 plus 111. And this will be equal to 1, 2, 3. Now, how do you do that? It's as simple. You're coming here, you say 1 times 24. 24 minus 3 over 2 times 40 is minus 60. 1 over 2 times 74 is 37. You come again, you carry out this arithmetic, you have 1. Minus 3 over 2 times 24, you have minus 36. 13 over 2 times 40, you have plus 260. Minus 3 times 74 minus 222. You carry this arithmetic, you have 2. 1 over 2 times 24 is 12. Minus 3 times 40 is minus 120. 3 over 2 times 74 is 111. You carry this arithmetic, you have 3. So this simply means that our x1 is equal to 1, our x2 is equal to 2, and our x3 is equal to 3. As simple as that. So you can see how we have been able to apply this to get the particular solution that we need. So now you can also use matrix in different ways. For instance, if I have 2a minus 0, 3, 3, 6 is equal to, maybe for instance, 4, 5, 1, 0, comma, find matrix A. It's as simple as ABCD. So you just come in, you just see your 2A is equal to, of course, this goes to the other side. This will be 4, 5, 1, 0 plus 0, 3, 3, 6. When you add this element together, 4 plus 0 is 4, 5 plus 3 is 8, 1 plus 3 is 4, 0 plus 6 is 6. So 8 alone will be equal to 1 all over 2 into 4 8s, 4 6. So this will be equal to, of course, we divide each of them by 2. This will now be 2, 4, 2, 3. That will now be matrix A. So you can see that it is as simple as that. You can do a lot of algebra with matrices and so on and so forth. So you can see the way we have been able to manipulate this simple one, 2a minus that. Of course, you take this to the other side. 0, 4 plus 0 is 4. You like simple matrix addition or addition of two matrices. 4 plus 0 is 4, 5 plus 3, you are adding corresponding element. 5 plus 3 is 8, 1 plus 3 is 4, 0 plus 6 is 6. And by doing that, you know, we are looking for A, not 2A, then this will be 1 over 2. You have that. You divide each element of that by 2. 4 divided by 2 is 2, 8 divided by 2 is 4, 4 divided by 2 is 2, 6 divided by 3 is 3. You can see how we have been able to manipulate matrices. You can see the usefulness of matrices, how this has helped us to solve all manner of problems. Real life problems can be modeled into system of linear equations, and the matrix inversion method is one of the methods that we use to solve a system of linear equations. Beloved, I believe you have learned one or two things from the class today. So we have come to the end of matrices, introduction to matrices. If you have any question, you can put it in the comment section. It will be attended to. And for those of you who have not subscribed to my channel, please subscribe to my channel. As you do, God will bless you richly on every side. Subscribe to my channel, click on the notification button, share my videos in your social media platform. And if you are an AI firm, I'll be looking forward to hearing from you so that I'll be part of those training your AI models with advanced mathematical algorithms so that your AI can be useful to the people of the world. Thank you very much for watching this video to the end. See you in my next class. Bye. God bless you.